Hi guys, so today we'll be solving the GFG POTD. The name is additive sequence. I will tell you what this question is all about. So it is stating that if we take any number in this series, it should be a combination of numbers before that. So if you observe this 3, it is a combination of these two, right? If we take this 5, it is 2 plus 3, correct? If we take this 8, it is 5 plus 3. If we take this 13, it is 8 plus 5, right? Pretty simple. So each and every number should be a combination of two numbers before it. So if that is the case, you have something called as, that is what they call as additive sequence. So how do we solve this problem? Okay, so here if you had, let's say 15, now 8 plus 5 is not 15, so it is violating the rule, right? So in that case, we will be giving out false. If we have an additive sequence, that means every element is a combination of two people before it, then we will say that, okay, this is an additive sequence, we will return true. So we will be starting with some previous one and previous two. Let us take the first element and the second element is previous, and we will start from here. Okay, we will start checking from 2 onwards. Now what happens is we will check. This is my 3. Okay, this is my element. Let me take it in a variable called as sum. Okay, let me take it in a variable called as sum. Now what I will do is I will check if my sum, okay, if my sum is actually less than P1 plus P2, right? If it is less than P1 plus P2, no, right? So we will see this condition. What is this condition like? But after this, what you can get is if sum is equal to P1 plus P2, okay, then this is actually satisfying. This is actually satisfying. So in that case, we will be now looking at this array. Okay, whatever this array will return. So it is kind of, you can say, recursion, right? So if I say that this was a call of solve P1, P2, and the index 2, then it will be calling this call, which is solve uh, P1, P2, and 3. But here P1 would be 2 and P2 would be 3. In the first case, the P1 was 1 and the P2 was 2, correct? So that is the case. Now, let's say if we came at fifth index, okay, you can probably see that the sum that I have right now is 1 and my previouses are P1 which is 5 and P2 is 8 which is 13, right? So my sum is less, so I actually want some more number of elements, right? So what I will do is I will do a I plus plus, correct? I will do a I plus plus. So my I would be over here. That is my index. I will do an I plus plus and I will also try to take this element. Okay, I will also try to take this element. So I will do sum is equal to sum into 10 plus whatever my A of I is. Correct? Whatever my A of I is. So after this, what will happen is you would get my sum to be equal to 13. Now your sum is 13 and you have P1 and P2, right? So that is fine. So again, you can go to the next solve call. But it might happen that you have something like 15. Okay, so you might have a number which is violating. So if you have such a thing, like sum is actually greater than P1 plus P2, then you can return a false because this is violating the rules, correct? Now there are some edge cases that you need to see. What if, what if my I is over here and my I wants to go over here to in order to fetch more number of elements, correct? In order to fetch more number of elements. So an example maybe could be so this is 8 plus 5. Maybe it is 11. It is less, right? So my sum would want more number of elements. So in that case, my I would cross this boundary. So if my I crosses the boundary, here I would write. So if I is actually equal to n, okay, so this is n, this is n minus 1. So if my I crosses the boundary, I would say that return false. Why? Because I have a less sum right now, and that is the reason I'm trying to make the sum more positive, right? Make the sum more positive. So, and I'm not getting it. I don't have any more number of elements, and that is the reason I now have to return a false, correct? So that is the case where, so I have shown you 5, 8, 11 case, 5, 8, 13 case, and 5, 8, 15 case, correct? So this is how it will behave. And also, if you check I++ is also happening over here. So it might happen that uh, in this, if sum is less than or equal less than or plus p2, I might go out of boundary. So in that case, what we can do is we will just check if my I is equal to, or we can say it is less than n, right? If I is less than n, then only you can add a sum, because if I goes out of the boundary, this will be a problem. Accessing a of I will be a problem, right? Now, one more thing over here is, instead of this if, you can have a while. Why? Because as I said, you can have like two, one previous and the second previous. And now you want to find out an element, like a number over here, which is actually equal to P1 plus P2, right? But what if it is less? If it is less, we have to take this digit. Maybe you would have to take this digit. Maybe you would also have to take this digit, right? All of these three digits you would have to take. So that is the reason I'm putting a while over here. So while you have a sum which is less than P1 plus P2, just keep on going. Just keep on adding that sum to, that those digits into your sum. Okay, and then there you would only have two possibilities. So either the sum would be equal or either the sum would be greater, right? So I have already explained you these two possibilities. Okay, now when do we terminate this thing? Okay, when do we terminate this thing? So if you have a solve call, here you are making a new solve call, right? And in that solve call, I will be, so let's just see this solve call. So in this solve, I will be passing previous 2 as my previous 1 now, and sum. This will be my previous 2 now, new previous 2. And I will be passing I plus 1. Okay, I will be passing I plus 1. So at the very start of recursion, I'm sorry, this is too messy, but I cannot really change everything right now. So at the very start of recursion, if I get I is equal to n, then at that point of time, I will return true, correct? So just check this out. Here in the, so here if you are in the stage where you are finding that the sum is less, right? And you are just trying to find a new member or a new digit. In that case, if you go out of bound, then that would mean that you don't really have any number, right? And you cannot make your sum, you cannot actually increase your sum right now. So that is the reason we are returning false. But the case over here is different. Somebody has called this solve call, and because it has been called, the sum is actually equal to P1 plus P2. So all the elements before that, they are actually behaving, or they are actually, I can say, they are relating, or the rules have been satisfied, correct, for all of these. So that is the reason, if in that case, if at the very start I am actually out of the bound, then I would return a true. Correct? That means each and every element in my array is actually behaving or satisfying the conditions. Correct? So that is the whole array. I know it is a little bit complicated, but I'm sure if you watch it again, you will definitely understand. So that is the whole call, right? Let's see how much time and all this thing will take, right? So if you see, we are just going once, right? We are just going once. over each and every element, we are just going once. So that is the reason we will take an order of n time. Okay, that is the reason we will take an order of n time. Now let me just show you the code for this. So if you see, in the main function, I will be calling the solve of first element, second element, and the ith node. Okay, so see the same thing that I have explained. If I is equal to n, return true. Else we have some elements, so that is the reason I will take the sum of sum is equal to a of I minus 0. So because this is a string, right? So this is the exact number which is there, minus 0 character. And while I do have my sum to be less than the two previous before, I will just do an I plus plus. Just make sure that my I is not crossing the boundary. If it is, then I don't have any more elements to put in my sum. So that is the reason I am going to return false. Else I will take that element, or I will just take that digit and put it into the sum. Okay. Now after this, you came out of the while loop because this condition has been violated. So there are only two conditions. Either your sum is greater, so that just means you're violating, so I will return a false, or it is equal. So if it is equal, I will just move on to the next solve call, right? So that is the whole thing. Now comes the main question. It might happen. So this is our thing, right? So 1, 2, 3, 5, 8, 13, and so on. So correct. For this, yes, the above algorithm will definitely work in order of n time. That is all fine. But you can also have an input like this 1, 48, 49. Correct. Now, if you start with 0 and 4, you're done. You will get a false answer. Correct. So that is the reason you have to start with all the combinations of previouses, all the combination of previouses. So I will definitely start with looking from 0 and 1 and then the whole array. Okay. But I will also have to check for 14 and 8 and then the whole array. And then maybe 1 and 48 and the whole array. So in this case, this is the combination that actually results in a true, right? So how many of these combinations can we make? So if you have something like 1, 2, 3, 4, 5, 6, 7, 8, so many elements you have, right? N number of elements. So let me put a I marker and a J marker. Okay, so let me put I over here and maybe J over here. Okay, and let me say that till 0 to I, let it be the starting previous one, and from I plus 1 to j, let it be a previous 2. Correct? Let it be a previous 2. And with this as P1 and with this as P2, you can use the above algorithm, solve algorithm, and this will take order of n time. Correct? To tell you the answer. So the question comes is how many of these combinations would exist? You can clearly see that I can go from here to totally to here, right? This can be a whole number. This can be a whole number, and then j can be over here. Okay, and then this could be the rest of the array. So your I will be going from 0 to n minus 2 almost, and your j will be going from I plus 1 to n minus 2. So clearly you can see this is order of n square. Okay. And in that order of n square also, if I let's say take 1, 2, 3, 4, 5, 6, 7. Okay, I take that my I is over here, j is over here, right? So now what I have to do, I have to take a k and run it over from 0 to I, and I have to put it into a num1, let's say, or maybe previous one variable, right? So first I will take the first digit, then I will take the second digit, and then I will take the third digit. Correct? So this will take n time. Again, I will go from k I plus 1 to j, and I will have my previous two. That will be 4 and 5. So again, this will take kind of n time. So again, I will be having like k is equal to 0 to I, and k is equal to I plus 1 to j. So this will give me my previous one, and this will give me my previous two. And after I get one of my previous is. This is one combination of previous one and previous two. After I get that, I will do a solve call on that previous one, on that previous two, and then starting from the next node, which is j plus 1. This is the whole thing, right? J plus 1. So as we already saw, this thing is actually going to be order of n time, right? And this is order of n square. So what is the total time? Order of n cube. That's it, right? One more question stays unanswered, that you are using recursion, so and this is going I plus 1, from I to I plus 1 and so and so. So you are actually taking order of n space, right? But if you carefully observe that recursion, I will just tell you. See, if you carefully observe this recursion is a tailed recursion. Okay, tailed recursion. That means the next recursion call is after this recursion itself. So you don't really need to preserve this recursion call. Okay, so in such cases, you can easily convert such recursions to a iterative recursion. So this is my iterative recursion. So I just copy pasted the whole thing. Okay, and the logic behind is there are only three lines that I have changed. Firstly, I have put a loop. Okay, and there are only three lines. So here you only see that in the next solve call. So in this solve call, I had previous one, previous two, right? But in the next solve call, my previous one is just updated to previous two. My previous two is just updated to sum, and my I is updated to I plus one. That's it. So in my next call, I'm just having this. So to just simulate the next call, I have added this while loop. That's it. Okay. So this is the iterative method. So in this iterative method, you are using order of one space. Okay. You are not using any extra space. That's it. Now coming to the main code. Main code, as I saw, as I already said, you will be having I is equal to 0 to n minus 2, j is equal to 0 to n minus 2. Why these two loops? Because you want to generate all the combinations, right, of previous one and previous two. So here, my previous one is num1 and my previous two is num2. Okay, so I'm going to have that previous one and then previous two. And if any of the solve calls are actually giving me true, then I will return true, right? And by default, if like all the solve calls that I try, I am not actually getting any of the any of the calls I'm not returning true, by default my answer would be false. Okay, so that is how it will work. I will just submit the code and show you. Correct. So you can see it is passing all the test cases. Okay, so that's it for this video. Thank you.